Hello. Okay. 3.6, the zeros of a quadratic function. All right, this one is particularly cool. I'm just warning you all. All right, so our goal is to be able to determine the number of zeros using 3 different methods. Okay, notice that I said determine the number of zeros, not determine the values of the zeros. Okay, so we just care how many, roots there are, because that's another word for zero. So really quick, I just want to make sure that we all know this. With a quadratic function, there are 3 possible cases in terms of the number of zeros, okay? So I can have, wow, that's a terrible axis. Ugh. But you get it. So if it's floating above the x-axis, it's not touching the x-axis, so there's no zeros. It also could be floating below, okay? I could have it such that the vertex is on the x-axis, little skinny one, okay? And then that's 1, 0. You can have that upside down doing the exact same thing. Or, let's give myself some more scrap paper here. I can have it cutting the x-axis, so it has 2 zeros, right? 1, 2. Or similarly, upside down, cutting x-axis 2. Okay, so we are looking to see which of these 3 cases we have when we have the quadratic equation, basically. All right, the first example, determine the vertex and the direction of the opening for each quadratic function and then state the number of zeros, okay? So essentially, this is just using logic to determine the number of zeros. So if we look at, we don't need that right now. All right, if we look at number 1a, this is actually, all of these are in vertex form, okay? So determining the vertex is relatively simple. Right? So our vertex is at, there's no h value, so 0 and then -5, right? That's where our vertex is. And then it's opening, it's positive, so it's opening up, okay? So I know that my vertex, because it's at a negative number, is below the x-axis and it's opening up, cuts it twice. Yeah. I don't really know anything about the stretch. I don't know where these zeros are, but all it asks me is to state the number of zeros. So, therefore, 2 zeros. Okay? E. I'm going to skip to these ones. If you would like to check your answers, do all of them and then check your answers on Schoology. I'm going to skip to E. All right, so also in vertex form, my vertex is at -3 and -5, okay, all right, a little v there, and then this one opens down because the a value is negative, so it opens down. All right, so I generally know, and you don't actually have to draw this if you can just think about it in your head, but I know that it is, my vertex is over 3, -5, it's about there, and it opens down. Okay, so it's both below the x-axis because of the negative, and it's opening down. So this is never going to touch the x-axis, meaning that, therefore, there are 0 zeros. Okay, so just logic. The next way that you can do zeros is by factoring. Okay, factoring actually finds you the number of zeros, finds you the value of zeros, but if you factor, you can find how many zeros there are, okay? So we've done a lot of factoring together in class. I'm gonna leave this for you guys. See if you can work on this. Check your answers on Schoology. Flip to the back. Okay. How can I do this without factoring or finding the vertex? There's a much simpler way. So to recap, we have no zeros, 1 0, 2 zeros, okay? We know that our zeros are at, let me use this little sheet here. We know that our zeros are always at the values given in the quadratic formula, because that's what it's for, right? So x equals -b plus minus square root b squared minus 4ac over 2a. This guy right here, okay? And really, our 2 zeros are at using the plus, so -b plus the square root of b squared minus 4ac over 2a and the minus, right? So the next one is at this value over 2a. Okay, So these are two distinct zeros. However, if the value that I was both adding and subtracting was the exact same, or sorry, it made this entire thing the exact same, it had no effect, our zero would be the exact same, which is essentially 1, 0. So what I'm saying is if this part here was equal to 0, then my 0 would just be the exact same, because it would be negative b over 2a and then negative b over 2a, which is the vertex, which is why, when we talked about it before, our x-coordinate of the vertex is at negative b over 2a. Okay, so if this is equal to 0, then 1, 0. Okay, the other situation. We often find that when this guy underneath the root sign is a negative value, we cannot continue because, of course, we cannot take the square root of a negative number. That's when you have no zeros. So if you can't do this, then there aren't any zeros. This case. And if you can, this case. If you want to summarize that, you can write it like this. Actually, you should write it like this. Ah. So if b squared minus 4ac, so that's what we had underneath the root sign here, is positive, so greater than 0, then 2 zeros. If b squared minus 4ac is equal to 0, 1, 0. If b squared minus 4ac is less than 0, then 0 zeros. This guy right here, b squared minus 4ac, is called the discriminant. That's the title. That's his little name. Okay? So on the next sheet, it says calculate the value of b squared minus 4ac to determine the number of zeros. I will do the first one with you, and then you guys can try to do all the other ones. So 3a. I know that 2 is a, 6 is b, and negative 7 is c. So b squared minus 4ac, negative 6 squared minus 4 times 2 times negative 7, 36 minus 7, positive 56. Actually, I don't even really need to calculate this because I already know it's going to be a positive number. But, okay, so this is a positive number. 92 is greater than 0. Based on our rules over here, if it's positive, then 2 zeros. Therefore, f of x has 2 zeros. So depending on whatever number you get here, you can decide on the number of zeros.